In this video, I'll demonstrate some of the things that can be done plotting data on computer monitors with the Specpr system. I've set up a directory that contains several Specpr files. There's a spectral library here and a working directory with some testing data. So these are pre-set up. Remember, I use an alias. So start Specpr, the developmental version, which has all the latest bells and whistles. Restart file R1 and an Xterm graphics window with double the default size. That's what we have here. So there are two ways you can look at data, and here's Spectral Library 06 from the USGS. You can do LW for list W. That's L followed by one of the letter codes assigned to the file, and you can list and page through. This is cumbersome, but if you know approximately where data are, you can maybe find it quickly. A simpler way would be to make a list file. So here's the Spectral Library 06 is here, and there is a list of the file already here. So we can just view that. And if you need to make that list, sp print the Specpr file name and direct it to list.txt or whatever you want to call it. But this makes it easy to find things. And I was going to start by displaying just a simple alunite spectrum. This is an interesting spectrum, so we get out of that. Remember, from program operations control, you can branch to math. T is to display, overlap on screen, transfer, which is a copy file, so T. And we've assigned splib06a to the letter W. So the spectrum that we want to plot is this one. So it's D1411. This is the record number for the wavelengths, D411, capital D6. And notice it has error bars, so we can include the error bars by typing an E here. Well, I made a mistake. I was talking W and I typed D, so it just shows that Specpr does error trapping as much as it can figure out what the user was trying to do. So W1411, W6, include error bars. Here's that plot. Now, if it didn't come up like it, you might have had a scale 0 to 2 or something, and so you can change scale, type in the vertical range, looks like 0.9, and this plot shows an interesting characteristic, that there are error bars here, but the error bars don't show up everywhere, and that's because they tend to be not much greater than the thickness of a 1 pixel line. So there are multiple line types that you can use in Specpr. So line type 0 is crosses with with no lines connecting the data points, and error bars are shown. You can see the error bars over here easier. Line type 1 is the same as line type 0, but connect the points. Line type 2 is line with no points and error bars are not shown. Line type 3 is connect the points. Do not show a little cross on the points, but do show the error bars when they become larger than a couple of pixels so that they can actually be seen. And to illustrate that the error bars are there, here's another property. We can zoom in. So we could type C. We'll actually do that this way. So let's go from 1.5 to 2.3. So wavelength 1.5, 2.3. Then we can auto scale the vertical, or we can set the range ourselves, like 0.1 to 0.8. So that got us in. And now notice some error bars are showing up, some are not because they're still too small. Another way you can zoom in is a capital S. This allows you to select the upper right and lower left points, and it expands the plot about that box defined by those upper right or upper left and lower right points. Now that we have a plot zoomed in, we can do some other things, and some of the things you can do here are described up here. G removes glitches. The glitch removal routine specifically tries to correct single bit errors. It's designed for raw data. This is not a raw data, so, and we don't have any glitches, so and it'll interpolate. Say this was a high point. It would look at the 2 points on either side and try and do a 1-bit correction that would bring it closest to the average between those 2 points. The interactive band analysis, capital A, so let's try that. We can change our scale more, but we've already done that here. So we'll go on to A, and here's where you enter your 2 continuum points. I'm clicking on this point right here, click. Then you have to go over to the terminal input box, press return, and then then you come over and choose your point on the other side, click on that, press return again. You get the continuum. Another return removes that continuum. It's a linear continuum. It shows you the continuum channels. Then it finds the several things. Here's the full width half max, the band center, which is a fit to the lowest points on the in the spectrum here, and this dashed line is the halfway point between the splitting the halfway point of the full width half max. You see that's offset from the actual band center. If we hit return one more time, we get the band center, the band width, that's the full width half maximum, the depth, so 36.84%, and the asymmetry. The asymmetry is the long side distance divided by the short side distance. Since this is less than that, the asymmetry is above 1. There's also some other factors here. The shoulderness is defined. That's so that you could, if you want to use these numbers, you can use them in tetraquarter. Okay, now you can also, if you accept all of that, you have options to redo everything here if you want to pick some things by hand. And if you want to save it, you have options to save that data to a text file. Let's get out of that. Now we're back to the main plot. The other things that you can do from here when you have a single plot up is look at all the information. So here's the header information that goes with the spectrum. So the title, the history, a manual history if you want to put more, who created the file. That's Greg Swayze at the USGS. These are bit flags for different indicators. Dates and times. Some of the bit flags will change the local civil time to universal time or whatever. So you have the date when the data was last processed and the date when data collection began. So all of this was done on November 22nd, 1985. Dates internally in the record are stored in Julian day. So there was never a Y2K problem with Specpr. There's a bit flag if this is an astronomical object. A bit flag is set here, which isn't appropriate for a lab spectrum, but it would give right ascension and declination. If it's a field sample, you can change the bit flag and put in the longitude and latitude of where the sample was collected. Band normalization in case the spectrum was normalized to 1 at some wavelength. These are parameters for spectrometers, so it depends on how that data was translated and put into these fields, the number of runs, and so on. The number of channels in the spectrum, the pointer to the wavelengths, pointer to the resolution, pointer to a text record describing further the data that's in record 1404. Incidence, emission, in this case it's an integrating sphere, phase angle is integrating sphere, and temperature. So all of those are part of the record for each spectrum. These can be changed, but in order to change them, you need to read the spectrum in, change it, and write it back out. And we only selected display, not to write out the results. So any change we did here would not have any effect on the data in the file. I'm not going to get into that at the moment. I'm going to concentrate on plotting spectra. So if we type G, we can go back to the plot. Now, let's, to zoom out, you do have to do that by hand. So 0.35 to 2.5 is the data range here. So I'm going to look at a couple of other spectra. For example, I'm coming down here to look at this. So this would show overlap. So OV1, overlap spectrum 1 equals W1425, and the wavelengths are 42, so W42. And we can choose to keep it the same, absolute levels, or we can do auto scale. And there's an advantage to both in certain situations. I'll leave it this way for now, and this shows you what we have, and here's the spectrum. And you can see that the match was over here, and if we change our range, 0.35 to, let's say, 4 microns, the data is very low out there, so it doesn't mean much. But you can see that we can look at the overlap region in more detail from there to, say, there. We can see that the black spectrum has low resolution out here, and the error bars get high as we get to 3 microns. The other spectrum is an FTIR. Notice we resolved this absorption band better. This is an FTIR spectrum versus a Beckman grading spectrometer spectrum. Why is the overlap different? It's because this is an integrating sphere for the Beckman and a biconical measurement of a small spot size for the FTIR. This is described in the documentation for the USGS spectral library. So for brighter things, so brighter wavelengths, the small spot size loses some photons out because the area of the circle that of the spot is very small. So some photons get lost from being counted. So as the signal gets brighter from multiple scattering, there's a greater departure. But where the signal is lower due to absorption in the sample, there's a better match. That explains that. If you want to, let's say you wanted to compare these two bands. So a better way to do that would be to autoscale. And you can autoscale or autoscale with a 2% buffer on the top and bottom. So if we do that, now they're autoscaled. So if we now zoom in and just zoom in from here to here, let's see, the auto scaling will be, it's controlled by different values here and here. So let's try changing that again, and maybe we'll get a little bit better overlap. Try there and there. Okay, now we get a little bit better overlap. Now we're not going to get a perfect overlap because the spectral resolution is different. You see, we resolved the minimum position better with the FTIR data, but it gives you an example of what you can do. Let's go back out. Now remember, this one's auto-scaled. You can turn that off, OV1 equals off, and then redraw. Okay, there are other line types too. Line type 3 is, yeah, we were on line type 3. Line type 4 is dashes. Line type 5, different length dashes. Line type 6, more different dashes. Line type 7 is small dots. So you can have different lines if you want to put on different data sets. I want to show some other ways to look at data. Often you're taking a spectrometer data in the lab or in the field or wherever you're taking multiple measurements. How good do those measurements agree? So let's exit here. And I'm going to look at this spectrum here, and so here's a sequence of red pellets measured with a Beckman spectrometer at 160 degrees phase. And this is with this file here, SPDO495. So we want D705, and this is an older listing, so it didn't include the wavelengths. We need to go and look at the wavelengths. So the wavelengths are in record 6. That's pretty common. That's my style, so you can choose wherever you want to put your wavelengths. Okay, so we can look at one spectrum here, and that's it. The spectra don't have, since they're the individual measurements, they don't have error bars on them. This is a little plastic pellet, so these are aliphatic hydrocarbon absorption bands from single bonded C bonds. Now, we've made a bunch of measurements, so we can look at all of those, and we can look at them in two different ways. So D, this first one, and we can do plus 999. So that'll go 999 records. It's not counting spectra, it's counting records. So you see that 7005 and then 7085, 7091. So each spectrum takes up, with 2151 channels, is taking up six Specpr records. So 999 will not get us 999 spectra. It'll get us 999 divided by 6, which is more than we need, because then it's going to transition to a different measurement. So let's just do this. So that's 1. We type E, and it shows the next. I'm typing E return, E return, E return. It's tedious. Another way to do that, there's also a history of, a history of what you did, so we can grab that. If we include an O, then it's in overlay mode. So now we just hit return, and notice over here it shows which spectrum was the last spectrum up and the title of that spectrum. So this number will match that number. We press return. Now it's 7091, 7091, and now both spectra are shown on here. And we can hit return, 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 return. And we can keep doing that. We see that the spectra are basically overlaying. There's a little bit of variation due to noise. This is a offset due to two different spectrometers. In the ASD spectrometer, it views the scene by fiber optics, and the fiber optics are split to 3 different spectrometers. This range over at 1.85 is another gap between spectrometers. So the signal is low there, and at the fibers are looking at a slightly different field of view, and since this is 160 degrees phase, there's a lot of shadows. So this spectrometer is looking at a slightly different field of view than this spectrometer, so it's common to see offsets in these kind of situations. What we would do would be to choose one of the spectrometers as a reference and multiply the other up, like to make this match there. That's a post-processing thing. But we can continue on, and now we've transitioned into another spectral measurement. So it shows that all our data are, there's no outliers, so we can average them all. So it's a quick and easy check of all your data. Remember over here, X is a hard exit, gets out. Let's try that one more time. So that was O. Now there's another trick. We can do a bunch of spectra. Now if we type E, it erases the screen and then continues overlaying spectra. So if the plot gets too messy, you type E and then continue on. Okay, now we've only been plotting spectra, but I wanted to show another thing that can be done. And you notice in this SPDO 495 file, measurements were made as a function of phase, and from there band depths were derived using the interactive band depth analysis routine. And so for 5 different, if we look at these down here, 5 different phase angles, we measured the band depth at 1.7 microns. That's this feature up here, as a function of band depth, as a function of phase angle. And so we can plot that. So we're plotting D756. In this case, the x-axis values are D7355. And now notice the name change down here from wavelength to phase angle. I'll show you how that's done in a minute. Now phase angle goes from 0 to 180, so let's change our range 0 to 180, and there's our, let's go back to L1. So here we see our those are pluses, those are not error bars. When there's a small number of channels, the cross gets larger, so the cross size is a function of how many channels you're plotting. So here we see that the band depth stays very constant until we get up beyond beyond 160 or so, 165 degrees phase. So that's interesting. So let me get out of that and let's just look at, now if you want to skip the plot, which in this case we're not going to have wavelengths because phase angles are the quote x-axis values. We want to go and look at just the information type I. And now we can see the title, where the data came from, and this is the key, a \W in line 4 of the manual history overrides the default wavelength label down here and gets put on the plot on the screen. Okay. Now I want to go back to the alunite 1411. So W1411, W6, and we have to change our wavelength range again. I accidentally changed the vertical scale, so let's change it again, W.3 to 2.5, 0 to 0.9. Okay, so we looked at overlaying other plots. You can overlay up to 7 different colored spectra, different colors for each spectrum, and auto scale them or not. But there's another thing, a capital G just reads out the graphics position. So like this position here, so the nearest channel is channel 313. The values of that channel are this, and the cursor is at a different, slightly different value. So for example, if we were trying to estimate the continuum, let's go and use this feature, and it's best to zoom in if you're trying to do something precision. So I'm gonna, to get out of this, you right click the mouse. So I right clicked in the plot, and that got me out of the capital G function. So I'm going to use the capital S, zoom in on the plot, and then back over here, I'm typing the capital G, and now I can read out positions. If I wanted to estimate, for example, where the continuum is up here, I'd once I had that position, so 1.764, let me get out of the capital G, right click, wavelength marker 1 equals 1.764. That puts a red line. There's wavelength marker 2, red, green, blue, and so on. Or actually, WM2 equals, let's try 1.9. I think it's red, blue, green. Okay, so let's go back to the capital G function. So if we just estimated here, we could, put a ruler up to the screen and get a little better estimate. And I click here. Now we see both have pretty close to the same wavelength. So the actual point and my cursor position. And here we see that the point is at 0.329, but the cursor position up here was at 0.515. So you can do a lot of work with the graphics cursor and these kind of things, and the wavelength markers help. Oops, come over here. One thing to be careful of, if I clicked and I'm not in the graphics mode, if I click here, I clicked like 4 times. Now I type G, and those 4 clicks have all been saved in a buffer. We need to figure out how X-Windows flushes the buffer before we enable the G function. If someone knows that, let me know and I'll add it in. But If you click, it's saved in a buffer, so if you click too much, you might get confused, and it's probably best to exit Specpr and restart so that buffer gets cleared. Otherwise, you can click around and get band positions just fine. If you click outside the plot window, then you get an out of bounds. So I'm going to right click to get out of that. Okay, that's a good overview of plotting. You can plot many spectra. The overlay functions help. There's functions, if you go through the messages on how to you can plot band depths or have band depths up here. Let's actually do a couple more things. Let's add this one in. So let's see, v1 equals on. Is it on, or did I exit it? Let's just put in a new OV1 equals W1425, W6. Oops, nope, it's W42. And let's auto scale it. Now let's do 1468. Let's see, does that? Okay. Oops. OV2 equals W1468, W22 auto scale. Okay, so you'd see for this spectrum, it's a noisier spectrum. We'd have to look at why, but it's obviously high resolution. It's an FTIR. It's probably using a different wavelength source, or is it a? Anyway, let's not worry about that right now. So one other thing you can do is show all, and it shows what OV1, OV2, and your wavelength markers are. So that helps if you're making a plot. You can, with a lot of spectra, they each get labeled, and you can do a screen dump of that and ship it off to colleagues. The wavelength set in use is for the black spectrum, and the title here is for the black spectrum. So all the spectra that are on the plot are labeled in this mode. Okay. With that, we'll exit. It's a good introduction to plotting capabilities in Specpr. Thank you for listening.